So the boron halides, their properties tend to reflect their molecular weight. As you go up in molecular weight, then you get a situation where you have a more or less and less volatile material. If you were to do a VS-EPR analysis on the boron halides, first of all drawing a Lewis structure and then using that to predict the shape of the molecule, then you would conclude that all the boron halides would be trigonal planar in shape, and indeed they are. Now, all of these boron halides have different Lewis acidity. The trend in Lewis acidity that you observe is not perhaps the one that would be first intuitive to you. So if we were to just consider the electronegativity of the halide atoms, which is the most electronegative halide atom? So fluorine is the most electronegative. So in terms of exerting inductive effects, fluorine has the strongest negative inductive effect, pulling electron density away from the boron. So you might therefore expect boron trifluoride to be the strongest Lewis acid and boron triiodide to be the weakest Lewis acid. But actually, if you do the measurements, it's not the case. The trend is in the opposite direction. Boron triiodide is the strongest Lewis acid, and boron trifluoride is the weakest Lewis acid. So a simple inductive argument doesn't explain this trend in Lewis acidities. In order to consider or to explain the trend in Lewis acidities, we have to look a little bit beyond our simple VS-EPR trigonal planar model of the molecules. But let's start off with that point. Here is boron trifluoride. Boron trifluoride is trigonal planar, has an sp2 hybridized boron atom. Because it has an sp2 hybridized boron atom, we know that we're going to have a p orbital, of which I've only drawn one lobe here, but we're going to have a p orbital above and below that trigonal plane. So you have a vacant p orbital, meaning the thing is a Lewis acid. This is what's responsible for the Lewis acidity of these boron halides. But that vacant p orbital has just the right symmetry, just the right shape in space to overlap with the lone pair orbitals that are present on the halide ions or the halide atoms. So we have fluorine. How many lone pairs are there on this fluorine? Absolutely, there are 3 lone pairs on the fluorine, of which I've only drawn one of them. I've drawn the one that has the most obvious symmetry overlap. So if you have a fluorine lone pair with this symmetry and a p orbital with this symmetry, you can get overlap between these 2 orbitals to form a bond. What sort of bond? Would it be a sigma bond? It wouldn't be a sigma bond. Sigma bonds have cylindrical symmetry about the molecular axis. This bond is not going to have cylindrical symmetry about the axis. This bond is going to be a pi bond because we have a nodal plane about the interatomic axis here. So we have a pi-like interaction between the lone pair orbital and the vacant p orbital. So you have a pi bond type contribution to the boron-fluorine bond. So how strong a bonding interaction we get will depend on how efficient the overlap is between these orbitals. So if we look, and I've drawn these some trend-like scale here. These weren't drawn with any physical properties specifically in mind, but we can see that as we move from fluorine to chlorine to bromine, obviously those atoms are getting bigger, and therefore the size of their orbitals is getting larger. Whereas boron's not getting larger. Boron is the same size in all of these compounds. So the efficiency of the overlap is greater in the case of boron and fluorine than it is in the case of boron and chlorine than it is in the case of boron and bromine. So you are more effectively filling that p orbital with lone pair electron density in the case of boron trifluoride than you are in the case of boron tribromide or boron triiodide. And of course, if you fill the vacant orbital, then you are negating, ameliorating the Lewis acidity of your boron halide. So the explanation as to why boron trifluoride is the weakest of the Lewis acids is because the vacant orbital responsible for its Lewis acidity is filled with pi overlap from lone pairs in here.